In this video, we're going to review the atomic number, talk about mass number, isotopes, and figure out how to calculate atomic masses for all elements in the periodic table. We said that the atomic number is also Z, denoted by Z, and it is the number of protons that each element has in the periodic table. They typically increase by 1 as we move across the periodic table. The mass number, on the other hand, includes the number of neutrons as well as the protons in the atom. So mass number, which is denoted by A, is larger than the atomic number because it also includes the neutrons. Isotopes of an element are atoms of the same element, but the only difference is that they have differing numbers of neutrons. Remember that to be atoms of the same element, they have to have the same Z number, the same atomic number, or number of protons. But they can differ in the number of neutrons because neutrons are neutral and they occur naturally in nature. This is the how we're going to denote the identity of an atom. So we can have the element symbol written as an X. This could be any symbol in the periodic table. We will have on top, the top left-hand side will have A, which is the mass number, number of protons plus neutrons. At the bottom left-hand corner, we're going to have the atomic number or the number of protons. If you want to remember it this way, A comes before Z in the alphabet, so A is written on top, Z is at the bottom. A is also the larger of the two because it's the sum of protons and neutrons. If we know the atomic number and the mass number, we can figure out the number of neutrons of each element because we can take the mass number A, subtract the Z number, the number of protons, to get the number of neutrons. Let's look at hydrogen. Hydrogen has 3 isotopes. This is protium, or hydrogen, this is deuterium, and this is tritium. For the first isotope, we note that it's got 1 proton but no neutrons, and we denote it as 1, 1, because 1 plus 0 gives us 1. For deuterium, we have 1 proton and 1 neutron. The sum of the two, or A, will be 2. That is the mass number. Note that Z, or the number of protons, does not change. When we move to tritium, tritium has 2 neutrons. Therefore, it will have a total mass number of 2 neutrons plus 1 proton, 3. And the Z number, or the number of protons, the atomic number, doesn't change. As you can see, as we move from one isotope to the next and the next, all that is changing is the top number, the A number, the mass number, which is the sum of neutrons plus protons. Let's look at a sample problem. Determine the numbers of protons, neutrons, and electrons in each of the following species. So let's talk about A. We have chlorine, 3517. Note that the top number is A, the mass number, the bottom is Z, the atomic number. The number of neutrons is equal to the difference between these two numbers, A minus Z, which is 35 minus 17. that is 18 neutrons. We know that Z corresponds to the number of protons. So I have 17 protons in chlorine, and because this is a neutral atom, I will also have 17 electrons. For B, C, and D, you can work on these yourselves. You first have to determine what W is here, which is very easy to do because we learned in the previous video that the symbol will tell us, if you go to the periodic table and figure out what the element is, that will give us the atomic number of each. And once I know that, I know the number of protons, I know the number of electrons, and I can figure out the number of neutrons by taking the difference of these two. In the last one, note that you have carbon 14. This is another way to write, another configuration to write atomic and mass numbers. For carbon 14, this is the mass number, not the atomic number. But we know by looking in the periodic table, we have the identity of the element, so we can figure out what Z is. And therefore, we don't have to necessarily write that carbon has a Z number of 6. This 14 tells us that it's a mass number. Go ahead and work on the last 3 examples. Let's now talk about how we calculate the atomic masses of each element. The atomic mass is a weighted average. It is not a simple straight up average where you add up all the masses and you divide it by how many numbers you have. Let's look at an example with apples to try to maybe figure out what a weighted average is. We have here a Granny Smith apple that weighs 200 grams and a Pink Lady apple that is smaller and it weighs 150 grams. If I have one of each, the average mass is going to be 200 grams plus 150 divided by 2. So it's going to be 350 divided by 2, 175 grams per apple. Now what if I don't have one of each? What if I have only 2 Granny Smith apples, but I have 8 Pink Lady apples? Note that I have many more of these Pink Ladies than I do Granny Smiths. So that is going to be reflected in the average mass of the apples as well. Because these are smaller and I have many more of these than I do Granny Smiths, the average mass is going to be closer to the Pink Lady mass than it is to the Granny Smith. This is how I figure out then the average mass of these 10 apples. I take the 2 Granny Smiths, multiply them by their mass. Then I take the 8 Pink Ladies and I multiply them by their own mass. Then I add those 2 masses together and divide them by the total apples, number of apples that I have. And note that this comes out to be 160 grams per apple, which is closer to 150 grams than it is to 200 grams. And that is because I have many more Pink Ladies than I do Granny Smiths. So they are going to skew my average mass closer to their own weight than the Granny Smiths are going to. We use the same principle to calculate the atomic mass of the different isotopes of each element in the periodic table. Let's take a look. We measure atomic mass in atomic mass units. Atomic mass unit is the mass unit that we use to measure the masses of each atom of an element. We define this as 1/12 of the mass of a C12 atom. A carbon-12 atom has exactly 6 protons and 6 neutrons, and therefore one atomic mass unit is approximately the mass of one proton and one neutron. If we look in the periodic table, however, we will notice that the masses that are listed under each element in the periodic table are not integers. They're not whole numbers. They're actually decimals. Why is that? If I were to simply add up all the protons and neutrons in an atom and then divide it by the total number, that should give me exactly a whole number. But that is not the case. And the case, it is not so because we have different isotopes with different abundances for each element. Just like the Granny Smith apples and the Pink Lady apples are different isotopes of each element, and their masses are going to, so the average mass is going to be determined by how much of each isotope I have. The average atomic mass, therefore, so how much an atom weighs, is a weighted average which depends upon the percent abundance of each individual isotope of that element. This is the formula that we're going to use to calculate the average atomic mass. We're going to take the mass of the first isotope, multiply it by its relative abundance. Then we're going to add the mass of the second isotope, multiplied by its relative abundance, and so on and so forth, depending on how many isotopes I have. Note this is very similar to what we were doing with the apples, right? So mass of the first apple times its percent abundance, relative abundance, plus the mass of isotopes multiplied by its relative abundance, etc., etc. Let's look at an example. I have naturally occurring chlorine in two different isotopes, chlorine 35 and chlorine 37. These are the percent abundances of each isotope. So chlorine 35 is 75.78% abundant, whereas chlorine 37 is only 24.22. Now notice, just like the Granny Smith and the Pink Lady, I have more, I have 75.8% of chlorine 35, which means that my average mass is going to be closer to this number than to that, to 37. So let's use this formula here to determine the average atomic mass for chlorine. The first thing that we need to do is take these percent abundances and divide both of them by 100 to convert them to relative abundance. 75.78 divided by 100 gives me 0.7578. Now that I have relative abundance, I can multiply that by 35, or 34.9688 AMU. This is the mass of my first isotope multiplied by its relative abundance. Then I add the mass of my second isotope, which is 36.9659, etc., so close to 37, multiplied by the relative abundance. 24.22 divided by 100 gives me 0.2422. I multiply these two numbers, and these two numbers, then when I add those two together, I get approximately 35.45 atomic mass units. If you look in the periodic table, you will find that underneath chlorine, the atomic mass is 35.45, which is what we calculated. This is how every mass for each element in the periodic table is calculated. Let's look at some example problems then. Use the atomic masses on the periodic table to determine which one has a larger percent abundance. Looking at neon 20 or neon 22. Note that neon 20 is smaller than neon 22, and we're going to have to figure out from the periodic table which one of these two isotopes has a larger percent abundance. Well, if you look at the periodic table, we find under neon, we find that its atomic mass is 20.18. This number is much closer to neon 20 than it is to neon 22, which tells me that neon 20 has a higher percent abundance than neon 22. You can try B and C. So here is the indium 113. Here's the information you will need for that. And then here's the information you will need for copper. Let's look at the last sample problem. We have the percent abundance of two stable isotopes of copper, copper 63 and copper 65, and these are the masses corresponding to those two isotopes. And the percent abundances are 69.17 and 30.83 respectively. Determine the average atomic mass of copper. And lastly, we have percent abundance of two isotopes of nitrogen, 14.003 AMU and 15.00 AMU, with percent abundances of 99.63 and 0.37% respectively. Determine the average atomic mass of nitrogen.